So there are two steps for the proof of the Poincare duality. The first is finite and the infinite set. So this is given on page 247 of Hatcher, and it is best if you read the proof from the book after you listen to what I have to say. So you start like this. The first part is you use the 5 lemma. So we have already defined the duality map. Yeah, so we will say that 4 dualities are isomorphisms. As a result, the dm, which is in the proof which we want to prove, that is isomorphism, it is also iso. So let us use the 5 lemma first. So these two, part A and B, will be used in the proof when I write it down, but you need to understand this. So if you say that M is a manifold covered by two sets U and V, these two sets U and V are open, then by 5 lemma, if du, dv and du intersection V are isomorphisms, then so is dm. So there is nothing to prove essentially here. We will just draw the diagram where the 5 lemma is applicable, and you can see it yourself. So let us draw the diagram. So you start with U intersection V, go to the direct sum of U and V, then you go to the manifold M. So C essentially means we are talking about compact sets which we have obtained after applying the direct limit. Increase index by 1 and repeat. Now we have written the cohomology sequence above. Now we write down the homology sequence. The duality map we will have to draw later on. So yeah, that is pretty much it. So we have been decreased index by 1 in the long exact sequence of homology groups. So let us draw the duality maps now. So yeah, so between U and U you have du, between V and V you have dv, between M and M you have dm, and now you can clearly see how the 5 lemma will apply itself. So that is pretty much it. Part B is slightly more involved, and the idea is this. We have to take this sequence dm as a limit of isomorphisms. So it's limit of some isomorphisms dui. So you can now see that dui will be obviously from hckui to hn minus k ui. Yeah, just like du, instead of du above, make it dui. So notice that M is a union of the sequence of open sets ui's, and associated with each of these open sets is a map dui taking from H ckui to hn minus k ui. Just like above du, we have this map dui for each of these sets. So as a practice, you should just write down du1, du2, du3, just to keep this in mind, because we will be taking direct limit of them pretty soon. Okay, so let us write down one of these DUIs. So what is this group on the left side? As I said at the start of the slide, these compact cohomology groups, whenever we write C at the bottom, means that we have taken them from a limiting process. Now what is this limiting process which has produced these groups? Yeah, these groups. Now these groups come from the manifold, that is relative group of the manifold cohomology group HK M comma M minus K. Now how does it come about, this group? First thing is accession. Now from accession you can go from M comma M minus K to UI comma UI minus K. But then you can range K over the entire sets contained within UI. So you can end up at UI comma null set, which will be, and then take the direct limit. So yeah, so slightly making it more clear, you have these groups now, HCK, UI, yeah, so that is pretty much it. So the compact set, when we write HC, is precisely the limit. Now notice that this directed set UI, U1 is contained in U2 is contained in U3 and so on. This induces these groups now. HCKUI, HCKUI plus 1 and so on. Yeah, this is a completely separate process I'm going to write. Now since you have this homomorphism between these cohomology groups HC, which come from the directed sets U1 contained in U2 contained in U3, now you can take limit over them. Now if you take limit over that, you end up getting, yeah, take a limit over it, and if you take a limit over it, it is obviously isomorphic to the entire manifold. Why is it obvious? Because this increasing sequence U1 contained in U2 contained in U3 blah 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 ends up at M. So M is the largest set, so M contains everything. So now we have a crucial important link. We have somehow been able to construct this cohomology group HKCM, and we have linked it with direct limit. This direct limit, as you can see the map DUI, so you take all these DUIs, we can link HCKM with HN minus K UI. Now the question still remains is, how do we now link Hn minus K UI, the direct limit of Hn minus K UI, to Hn minus K M? Because this direct limit which I have just written, direct limit Hn minus K UI, this is nothing but direct limit of DUIs. Now this isomorphism is provided by proposition 3.33. And now we are done, because now you have, on one hand you have direct limit of, because if you see the bottom right corner, we have direct limit of HCKUI equal to HCKM. Now this direct limit HCKUI, it comes from DUI, yeah, which I have just underlined. So this DUI, you take it, you end up in direct limit of Hn minus KUI, which is isomorphic to Hn minus Km. So basically we have gotten Dm, which goes from cohomology group HK to homology group Hn minus K. First case we can prove the theorem is the manifold is equal to Rn. Now to prove this, you start with manifold Rn, you take a ball in Rn, and the first thing is we want to again construct these sets HC. Yeah, so as I mentioned before, every time you see the sets HC, that is H subscript C and some cohomology group, that means they have been formed from direct limit. So again, we start with manifold Rn. Take a ball in this Rn. Now we want to form these subscript cohomology groups. So you take a ball out of Rn comma Rn minus B. Again, make these increasing sequence of balls, take a direct limit, blah blah blah, get an isomorphism like this for all k. Yeah, you have fixed k, you are just ranging the balls. Okay, now we want to form a cap product. So we have to link n minus k and k. So consider the following cap product. Yeah, so this is the homology group in nth part. The second is homology group in the kth part. Notice that whenever you talk about Rn comma Rn minus a ball, what you are essentially talking about is a sphere. So for a sphere, the result is true only when the homology and the cohomology groups are 0. Then you get integers, non-trivial, and when homology and non-homology groups are also integers when you are in the dimension of the sphere, that is n. So it's trivial, non-trivial only for k equals to n. So in this case it is alpha here, say, which is a generator of this group. Yeah, this is a sphere, so the only thing it is non-trivial is when k equals to n. So these two parts will be non-trivial, and this will be H0 on the right hand side. So we need to show that alpha cap phi is the generator of H0. Yeah, we have to take n equals to k because that is the only case when we have both generators alpha and phi are non-trivial. Yeah, if even one of them is trivial, then you take cap product, it will be 0. So we want to show this is which is an element of ring R, where obviously phi now is element of var phi, or psi, I should say psi is element of H0. Yeah, so this is just 1. So yeah, just replace this psi with 1 and you just get this alpha cap phi is the generator. Yeah, this is the generator, and thus we are done. We have been able to get a generator, and therefore there is an isomorphism from hk to hn minus k. Yeah, that is pretty much it. So sphere has made our life really easy. So now we just use induction and finish the proof. So dm is an isomorphism for m for an arbitrarily open set in Rn. Yeah, so we have to show this. So you take an arbitrary open set and we should be able to prove it. We have already proved in the case 1 when m is equal to Rn. So we want to use induction. Yeah, in order to use induction, we will have to first express M as a countable union of sets. Obviously, if it is countable, only then we can use induction. So let us write this down. M is equal to union of these sets Ui, yeah, where this is a countable set. Now consider the sets Vi. So these are made up of one less set, j is less than I. Now the reason will become immediately clear because we want to use induction, so we have to use I minus 1 to go to I. So these Vi and Ui intersection Vi are unions of I minus 1 bounded convex sets. So yeah, so these Ui are all convex. So M is a union of Ui where each Ui is a convex set. And now we have come to the case I minus 1. Obviously induction means I minus 1 should give you I. So we have to do induction on the number of these convex open sets. So we can start with an assumption that dVi and dUi intersection Vi are iso. And we need to prove that dUi union Vi is an iso. So by the first part, dUi is an iso because manifold locally looks like an Rn. Yeah, so by part A, we have dUi union Vi is an iso. Okay, now since M, the way we have written, is an increasing sequence of VIs, yeah, so it's increasing union of VIs. This kind of proof should remind you of something we do for lim sup and lim in analysis. So we keep forming these increasing, we take unions that keep forming these increasing sequences. So now you use part B and say dm is an iso because each dvi is, yeah, in part B we formed this increasing sequence of sets u1 contained in u2 contained in u3, and we formed dm as a direct limit of duis. So here instead of ui we have vi, and we use the same thing. So for an arbitrary open set, we have been able to prove this by induction. So essentially the proof is by induction. Now part 3 is really easy. You just replace the bounded convex open set in Rn. Yeah, so you just repeat the argument above and replace bounded convex with open set in Rn. That is pretty much it. So again, the proof is by induction. You want to prove that it is true for any arbitrary open set. and you use induction to do so. So yeah, that is pretty much it. Yeah, so when we're talking about M as an arbitrary open set in Rn. Yeah, because manifold globally could be something different. So yeah, that is pretty much it. Please do read page 248 of Hatcher to have better understanding of this. So yeah, part 3 is just replace bounded convex where each UI is bounded convex. Yeah, M is equal to union of UI where each UI is bounded convex. So instead of writing bounded convex, you write open set, and that is it.